Okay, the last part of chapter 7, okay, which is a solid. Okay, now we want to see properties of the solid materials. Okay, and this solid is actually divided to two types. There are two types of a solid material. The first one is a crystalline solid. So this crystalline solid have a well-defined shape, okay, in which in the crystalline solid, the particles in it can be either atoms, molecules, or ion, depends what is the substance of that solid. The atoms, molecules, and ion, or the particles, okay, in general, in this crystalline solid are in orderly arrangement. Okay, it has a well-defined shape, and the arrangement of the particles in this crystalline solid are in order. And then the second type of the solid material is the amorphous solid. Okay, so this amorphous is opposite to the crystalline solid, in which this amorphous solid has a poor defined shape. Okay, in which the particles in this amorphous solid, we know that the particles can be atoms, molecules, or ion. Okay, so the particles are lack in orderly arrangement. They are not in orderly arrangement. Due to this properties, this difference between crystalline and amorphous solid, then we will focus our discussion, okay, after this on the crystalline solid. But you need to be able to describe the difference between crystalline and also amorphous in terms of their shape and also the particles arranged. Okay, so what is the crystalline solid? Okay, or what is a crystal? Okay, so crystal is actually consists of the atoms, molecule or ion that are arranged in orderly repeating pattern. Okay, and this orderly repeating pattern extend in all three spatial dimension. Okay, means that it is increases to the side, okay, and then up and down, to the front and to the back. Okay, it is 3D. Okay, so these are the examples of the crystal. Okay, the natural crystal, okay, that we have in the earth. Okay, there are so many colorful crystal, so we can accept this as a crystal, right? However, before this, we don't know that the sodium chloride that we use in our kitchen also one of the crystalline solid. Even ice, okay, that we drink every day, ice is also one of the crystalline solid. Okay, due to the criteria of the crystalline solid that their particles or their molecules in orderly arrangement and repeated. Okay, so the crystalline solid start with the basic of what we call as a unit cell. Okay, so the unit cell is the basic repeating structural unit of a crystalline solid. Okay, to have a large crystalline solid, it is actually start with one unit cell. Okay, so this is a unit cell, a cube. Okay, and each point here, okay, each sphere here, okay, represents an atom, ion, or molecules. Then it is known as a lattice point. Okay, so when we have one unit cell, okay, that is repeated. So we observe that we have another unit cell at the back, another unit cell at the side, another unit cell below it, okay, below to the right, okay, and so on. It is keep on repeating. Coordination number defined as the number of atoms around one atom in a structure, in the structure of the crystal. Okay, and this value of the coordination number will then determine or indicate, okay, how tightly an atom are packed together. The value of the coordination number will tell us whether the crystal is packed or it is less packed. Okay, so the larger the coordination number means that the closer the atom to one another. Okay, we just need to be able to differentiate when the coordination number is high, means that the structure of that crystal is more packed. Okay, and if it has less coordination number, means that our crystal is not so packed. Okay, so there are three types of the unit cell that you have to be able to identify and also to draw it on your own. Okay, so the first type of the unit cell is a simple cube. So simple cube is when we have a cube, okay, and then we have particles at the edge of the cubes. Okay, we know that in one cube we have 8 edges, 8 corners, right? Okay, so we have a particles at each corners, at each edge of the cube. So, okay, when we have a particles at the corner, okay, it is actually being shared with 8 unit cells. At the edge of one unit cell, at the edge here, okay, one unit cell only belongs 1/8 of the atom. Okay, only 1/8 of the particles at the corners that is belongs to this specific unit cell. Okay, so if we calculate how many particles per unit cell of simple cube, okay, so that it will be 1/8, okay, 1/8 because each corner only has 1/8 of the particles belong to that unit cell, multiply with 8 corners that we have all together, or 8 edges. So the number of atom per unit cell of simple cube is actually equal to 1. Only 1 atom per simple cube. Okay. And then the second type of the unit cell is the body-centered cube. Okay, so this body-centered cube is the same as the simple cubic when we have particles at each corners or each edges of the unit cell. Okay, but the difference in this body-centered cube is when we have one particle at the center of the cube. Okay, so one particles at the center means that, okay, these particles at the center belongs to this unit cell only. Okay, so if we calculate how many atoms per unit cell for the body-centered cubic, okay, so we will calculate how many atoms at each corner. So 1/8, okay, multiply with 8 corners that we have, plus with, we have 1 atom at the center. So altogether we have 2 atoms per unit cell of body-centered cube. Okay, so look at to the coordination number of this body-centered cube. The Cn is 8. As for the simple cube, just now coordination number is 6. It means that body-centered is more packed than the simple cube. Okay, and then now let's look at to the third type of the unit cell, which is the face-centered cube. Okay, so this face-centered cube, okay, have the same particles, the same number of particles at each edge, okay, at each edges of the unit cell of the cube, okay, and it also have particles at each faces of the cube. Okay, so we know that in one cube we have 6 faces, right? Okay, so we will have 6 particles at the faces of the cube. Okay, and we know that when we have particles at the faces, at the face, okay, of a cube, it is actually being shared with 2 unit cell. Okay, shared with 2 unit cell means that 1 unit cell only have half of the particles, okay, at one face. Okay, if we want to know how many atoms per unit cell, then 1/8 multiply 8, that is for the particles at the corners, and then 1/2, okay, multiply with 6 faces of the cube that we have, okay, so that it will be equal to 1, equal to 3, so the total will be 4 particles per unit cell. Okay, then we look at to the coordination number, see that this face-centered cube have a highest coordination number, means that it is the most packed one as compared to the other two. So let's try to draw the unit cell. Okay, start with your cube. Okay, so this is our 3 cube. Let's start with the simple cube. Okay, and then we have a body-centered and face-centered. Okay, so for the simple cube, you will have 8 particles at each edge. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then for the body-centered, we have the particles at the edge as well. Okay, it is just we have another 1 particles at the center. Okay, and then for the face-centered cube, the particles at the edge, okay, the examiner will calculate, is that enough particles? Okay, you are supposed to have 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then the particles at the face, the back one, the upper one, okay, the side one, below one, the front face, the side face. Okay, so 1, 2, 3, 4, 5, 6. Okay, so calculation of the number of particles per unit cell. This one will be 1 over 8 multiplied with 8 corners, so that it is equal to 1 particle per unit cell. Okay, as for this, it is 1 over 8 multiply 8 corners plus with 1, okay, at the center. So total will be 2 particles per unit cell. Okay, and for the face-centered cube, okay, it is 1 over 8 multiply 8 corners, okay, plus with 1 over 2 multiply with 6 faces. So altogether is 4 particles per unit cell. So finish with the basic of the unit cell. Now we want to go to the type of the crystalline solid. Okay, there are 5 types of the crystalline solid that we covered in our syllabus. Okay, I hope that you refer it to your textbook. It is in the page of 506, okay, until 508. Okay, only 3 pages about the 5 types of the crystalline solid, included the figures there. There are so many figures there. These are all the list of the crystalline solid. The first one is the atomic solid. Okay, look at to the name, it is atomic solid. Okay, and then we have a molecular solid, of course, that you can differentiate between atoms and molecule, right? Okay, and then we have an ionic solid. Okay, we have learned this in the ionic compound. And then we have a network covalent solid or giant covalent solid. This might be new to you. Okay, and finally is the metallic solid. Metallic also we have learned in the metallic bond. Okay, out of these 5, okay, we have familiar with except for the 4th one. Okay, so let's look at it one by one. The first one is the ionic solid. So this ionic solid consists of the ions, which is cation and anion, in which these two type of ions, positive and the negative ion, are held together by the ionic bonds. So example of the ionic solid is the sodium chloride. Okay, not just sodium chloride, all ionic compound, they are ionic crystalline solid. Okay, for example, MgO, Al2O3. Okay, because we know that all the ionic compound, they are also solid at the room temperature. So either they are solid or not solid at the room temperature. When we discuss on the solid subtopic, okay, we talk about them when they are in a solid state. Okay, but it is obvious for the ionic compound, they are all solid at the room temperature. So this ionic solid have a high lattice energy, so that they will have a high melting point and boiling point. Okay, it is hard to break the ionic bond to boil them. Okay, so they will have a high melting and boiling point for ionic solid. And then the second type of the crystalline solid is the atomic solid. Okay, so the atomic solid, okay, is the solid when we have atoms that held together by the dispersion force. Okay, we know that the atoms, okay, they, of course, that they don't form any bond, so they are not polar. Okay, they are non-polar. They are only having London dispersion force as the interparticle forces. Okay, as what we have learned, dispersion force exists in all atoms and all molecules. So for these atoms, example, group 18, okay, for the noble gas, group 18, they are exist as atom. Okay, so when they are exist as atom, okay, the force that attract them together, that held them together, is only London dispersion force, and we know that this is a weak force. Okay, that is why the melting point and the boiling point of the atomic solid, most of them are very low, okay, except for the large atoms. Okay. And then the type of the unit cell, okay, for this atomic solid is the face-centered cube. Okay, so we can look at to the textbook. Okay, face-centered cube. It is in the page of 506. Okay, figure 12.3. Okay, that is the unit cell of the argon. The unit cell of the argon, and it mentioned there that it is a face-centered cube for the atomic solid. The next type, okay, or the third type of the crystalline solid is a molecular solid. Okay, it can be for a small molecules or the large molecule. Okay, and the molecules are held together by the intermolecular forces. The intermolecular forces depends on the molecules. If it is a non-polar molecule, for example, oxygen and iodine, they only has London dispersion force as their intermolecular forces. But if we have polar molecules, for example, SO2 molecules, these SO2 molecules, when it turns to solid or crystalline solid, the type of the intermolecular forces that held it is the dipole-dipole force and also London dispersion force. But for the molecules that can form hydrogen bond like H2O and ammonia here, okay, the type of the intermolecular forces that held them are dispersion, dipole-dipole, and also hydrogen bonding. Okay, see the example is given here in this figure. We have a molecules of H2O and then the other molecules of H2O. So the type of force that bind them, okay, that makes them become a solid is actually the hydrogen bonding. Okay, and of course the presence of the dispersion force. Okay, so the force that attract them together is the intermolecular forces. We also have this molecular solid for the big molecules. Example that is given here is the Ne molecules. Okay, but still under the category of the molecular solid. The fourth type of the crystalline solid is a network covalent solid. Okay, it is composed of the atoms, okay, that are linked together by the covalent bond. Okay, and that is why we have a covalent term. Example of the network covalent solid is the diamond, graphite, and the silicon dioxide. Okay, so let's look at to the diamond structure. Okay, why it is known as a network covalent or giant covalent solid. Okay, so one particles here consists of carbon. Okay, it is actually a carbon that is attached to another 4 neighbor carbons in a tetrahedral arrangement. See the arrangement? Because we know that each carbon atom has 4 valence electron. Okay, so carbon can form 4 bonds altogether. So now when we look at to one carbon atom, it's already formed 4 sigma bond with 4 neighbor carbon. So it means that all the valence electron of the carbon used in the formation of this bond, so that the carbon are forming sp3 type of hybridization. This is if we refresh back the information on the hybridization. Okay, and the other carbon atoms also form covalent bond with another 4. Okay, so look at to this carbon atom. Okay, it is attached to this carbon, this and this carbon. So one carbon will attach to 4 other carbon. Okay, and this attachment, okay, will continuous on and on in the 3 dimension. Okay, that is why this diamond or the network covalent solid is also said to be not a molecule. Okay, because the number of the atoms joined up in a real diamond and graphite is completely variable. Okay, the number of the carbon is not fixed. If we said that it is a molecule, for example, we have a molecule of the C2H4. Okay, so it is fixed. The number of them in this molecule will be 2, and the number of the hydrogen in this molecule will always be 4 per molecule. Then we call it as a molecule. But since that the number of atoms here is varies, so it is not known as a molecule. Okay, and the number of the carbon atoms, okay, in a sample of the diamond will depends, will be depends on the size of the crystal. The more carbon that we have means that our diamond is bigger. The less carbon that we have means that we have a small size diamond. Okay. And then the second type, okay, of the example for the network covalent solid is graphite. Okay, graphite is the allotrope of carbon. Okay, it is the same as the diamond just now, in which each point here, each particles here are actually carbon, in which one carbon form bond with 3 neighbor carbons. Okay, remember just now carbon has 4 valence electron, means that carbon will form 4 bonds, okay, with 4 valence electron. Now when we look at to the structure of the graphite, each carbon form bond with 3 neighbor carbon. It means that each carbon will have 1 delocalized electron. Okay, it will have a multiple bond there. Okay, it will have a delocalized electron. Okay, and due to the presence of this delocalized electron, okay, then it will make the physical properties of this graphite, okay, little bit different from the diamond just now, in which the graphite can conduct electricity, okay, but not the diamond. Okay, diamond is not the electrical conductor, but graphite, yes. Okay, this is because the graphite has free moving electron or delocalized electron that can transfer the charge. Okay, and these carbon are forming sp2 type of hybridization. Okay, that's the difference between the carbon in diamond just now. Okay, when it forms sp2 type means that it has a delocalized electron, it can carry the charge, it can become a good electrical conductor. Okay, so when we come back, okay, to the structure of this graphite, when each carbon are attached to 3 neighbor carbon, okay, we extend the structure, then we will have like the hexagon layers, right? Okay, this is a hexagon. One hexagon connect with another hexagon. This is actually one sheet of graphite. Okay, and then we have another sheet of graphite, and between this sheet of graphite, they are attached together by a weak van der Waals force. Okay, so weak van der Waals force, it means that, okay, it is easy to break this weak van der Waals force. Okay, that is why graphite can be used in our pencil. Okay, it is used as a pencil lead, right? So we also have a layers. Okay, above here we have a layers of the graphite. Below here we also have a layers of the graphite, in which each layers are connected by the van der Waals force that is weak. Okay, so that when we use it as a pencil lead, okay, bila kita goreskan kita punya pencil tu, okay, bila kita shadekan kita punya pencil tu, then the layers of graphite tu yang menyebabkan ada tulisan dekat kertas kita tu lah. Okay, because bila kita gores tu, we give some force, right? Okay, kita bagi some force untuk breakskan the weak van der Waals force tu. So tulisan yang kita nampak dekat kertas tu is actually the graphite yang dah terputus dia punya van der Waals force. Okay. As compared to diamond kita tak boleh guna as pencil lead kan? Sebab what we don't have a weak van der Waals force. We have a strong, they are all the covalent bond. Okay, that is hard to be break. Okay, that are the 2 allotrope of carbon. Okay, for these 2 allotrope of carbon, I want you to refer to your textbook. It is in the page of 508, diamond versus graphite. Table 12.6. That's the difference, okay, between graphite and diamond. Okay, why we compare graphite and diamond? Because both of them are allotrope of carbon. Okay, look at to their density. Okay, page 508. I hope that you are referring to your textbook because I don't have this table in my slide. Okay, so table 12.6, we look at to the density. They have different density. Diamond is more dense than graphite. Okay, hardness also different. Okay, graphite is very soft. Okay, that is why it can be used as the pencil lead. Okay, as for the diamond, it is the hardest one. It is so hard. Okay, and then the melting point are the same. Okay, look at to the color. Okay, shiny black for the graphite and colorless or transparent for the diamond. Okay, electrical conductivity. Graphite can conduct electricity but not diamond. Okay, and then we look at to the enthalpy change for combustion. If we combust them, okay, 1 mole, okay, the energy is almost the same. Okay, that is the important properties of the diamond and graphite that you should remember. Okay. Now we move to the last type of the crystalline solid, which is the metallic solid. So this metallic solid is a closed packed structure. Okay. Of course that we have a metal, they are naturally exist as a solid at the normal temperature at the room temp. Okay. And this metal composed of the atoms of the same metal that is linked together by metallic bond, so that the interparticle forces will be metallic bond. Okay, so example of the metallic solid are all metals. Okay, sodium, magnesium, iron, chromium, aluminium, even the aluminium foil that you have in your house. Okay, the aluminium foil that you have, it is also a crystal. Okay, before this we think that crystal is just used in the jewelries, right? Okay, but the crystal behavior, the characteristic of the crystal that is start by the basic of the unit cell and it is repeated with the orderly arrangement of the particles, that is actually the criteria or the characteristic of the crystal made the all metals, okay, even the salt as a crystal, okay, even ice a crystal. Okay, then I want you to refer to your textbook, okay, page 505. Okay, it is a comparison between the characteristic of all type of the crystalline solid. This is a table 12.5. So if we look at to the table, okay, it is almost the same as what I have here. Okay, but it like another one type of the crystalline solid, which is the atomic solid. Okay, so let's refer to the textbook. Okay, we have the atomic solid. So you have to know what is the particles. Okay, at the lattice point for atomic solid is atom. Okay, interparticle forces is London dispersion force only. Okay, and then the physical properties of this atomic solid is a soft, very low melting point, and then it has it is a poor thermal and also electrical conductor. Okay, and example is given there for the noble gas element. And then the second of the crystalline solid in this table 12.5. Okay, the particles at the lattice point is the molecules. Okay, we can look at to the example of the particles at the lattice point for the molecular solid. It is in the page of 506. Okay, when we observe that in one particles there is actually consists of molecules. Okay, look at to figure 12.31. Okay, so that 12.31 is the face-centered cube of the methane, CH4. Okay, so in one particles, it is actually consists of a molecule of the CH4 there. Okay, so the particles is the molecules, interparticle forces will be dispersion, dipole-dipole, or hydrogen bonding, or all. Physical properties, it is fairly soft, low to moderate melting point, poor thermal and electrical conductor. They are not electrical conductor. They are not a good thermal and electrical conductor. And then the third type of the crystalline solid is the ionic solid, when the particles at the lattice point are the anion and cation. Okay, the type of the interparticle forces, ion-ion attraction, or you can write it as the ionic bonding. Okay, and then the physical properties, you have to remember the physical properties. We also have discussed this in ionic bonding, that they are hard, they are brittle, rapuh. Okay, they have a high melting point, they are good thermal and electrical conductor when they are in a molten state, in a liquid state. Okay. And then the fourth type is the metallic solid. The particles at the lattice point is the atoms, interparticle forces, metallic bond. Okay, the properties, it is soft to hard, okay, low to very high melting point. They are good electrical and thermal conductor. They are malleable and ductile. Okay. And then the last type is the network covalent solid. Okay, the particles at the lattice point are atoms. The interparticle forces, of course, they only have a covalent bond. Okay, and then the physical properties, they are very hard, okay, but soft for graphite. Okay, there is a difference there. Okay, not all network covalent solid will have the same properties. Okay, in general, they are very hard, but graphite is soft. Okay, and then they have a high melting point. They are usually poor thermal and electrical conductor. That this is a criteria of the diamond, but not the graphite. Graphite is a good electrical conductor. So in principle, okay, solid, liquid and gas, okay, they can be converted to each other. Okay, if we have a liquid, okay, that turns to gas, so that we call this process as the vaporization process. They are vaporized. Okay, and then when we have a solid particles, okay, turns to liquid particles, okay, we said that these particles undergo melting process. Okay, but reverse process from liquid turns to solid. Okay, we call this process as the freezing process. As when gas, okay, return back to liquid, this is what we known as a condensation. Okay, as for the solid to gas, okay, directly from solid turns to gas, it is sublimation. Okay, and from gas back to the solid, it is known as the sublimation as well, or we also can use the term of deposition. Okay, they can be converted to each other state. Okay, it is just about the condition. It's either you need the temperature to be high, or the temperature need to be low, or the pressure need to be high, or the pressure need to be low. Okay, they are all can turns to solid, since that we are discussing about solid. Okay, it is just how they can turn to solid. If let's say we talk about gas, okay, the gas that are present as gas at the room temperature, example of the oxygen, okay, we don't say that, oh, it will never be a solid. Okay, it is just about the condition that is needed for them from gas to turn to solid.